Hello everybody. In this video we are going to discuss one very common case that we deal with in case of chemical reactions, which is dealing with multiple reactions. And it's very common that or it's one of the common cases of having multiple reactions is to have a reaction that is desired. For example, let's take this reaction here for the dehydrogenation of ethane to produce ethylene. So this is the main goal of the whole reaction, or the whole, or the unit or the reactor that we have, is to produce ethylene and hydrogen. Of course, hydrogen would be another product that we are producing, by the way. But this is what we want to produce here, is ethylene. And to produce the ethylene, we need to adjust the reactor conditions of pressure and temperature so that the reaction will take place and the ethylene is produced. However, under the same conditions, there is a possibility that other reactions would take place. So the same reactions that promote this, or the same conditions that promote this reaction, are going to be suitable for another reaction, or will promote another reactions. For example, that the ethane will react with hydrogen to produce methane, or that the ethylene that's produced react with ethane producing propylene and methane. So these reactions are undesired reactions. It's not why they're not the reason why we made the reactor. They are reactions that are called side reactions. So this is not something I would like. That's why the ethylene and hydrogen are called the main products. Methane and propylene are called side products. Then this is the main reaction, and these are the side reactions. There is one other thing that we want to mention about the dealing with multiple reactions, is that we can deal with multiple reactions the same way we deal, or chemical reactions the same way we deal with algebraic equations. So for example, if we have the dehydrogenation reaction that we just mentioned, and we have the side reaction, these are two different reactions. We can come up with a new reaction that is the result of adding the two reactions. So if we add the two reactions, then we will add the left hand side components, and we will add the right hand side components, and this is going to be a new reaction. So we have ethane plus ethylene goes to ethylene plus hydrogen plus propylene plus methane. We have here two ethane, so it's going to be 2 instead of having each one separate, and we have here ethylene in the product and the reactant, so they will cancel each other, and now we have a new reaction. So what we said before about the chemical about the mathematical equations, the algebraic equations, when we were talking about the independent equations and the degrees of freedom analysis, applies here as well. So what we have here are actually two independent chemical reactions. The third reaction is a dependent reaction, so we don't consider this as a new reaction. So this was one other thing that we need to know about the dealing with chemical reactions. But let's go back to the point of having main reactions and side reactions. I'm sorry. In this example that we just discussed. In this case, we have kind of deviation from the ideal case. So it's something that we have been going through since we started this part of the chapter, that there is an ideal case, and the ideal case in most of the cases doesn't happen, and then what happens in reality is a deviation from the ideal case, and because of this we define a parameter that explains how far we are from the ideal case. For example, when we discussed about giving the feed to the reaction, and that we ideally will be providing the feed with the same stoichiometric ratios, and then we found out that this is not the case in many reactions, and that we provide the feed with different ratios. and this led to the presence of what we call the limiting and excess reactant. So we came up with a parameter that's called the fractional excess to tell how far we are from the ideal case. Also, in case of having the limiting reactant not being 100% consumed in the reaction, this was a deviation from the ideal case. So we defined the fractional conversion to account for or to be a measure of how far we are from the ideal case. So also here we have another situation. So in this situation we have an ideal case where the reaction that we want is only the main reaction, but we have another side reaction that takes place, and this side reaction is undesirable reaction. So ideally I would like to have the main reaction only taking place, but actually there are side reactions that are taking place which I don't like or I don't want to happen. So we want to define, or we will define, parameters to account for this deviation from ideality. So these parameters that we are going to discuss are actually two parameters. One of them is called the yield and the other is called the selectivity. So let's start with the yield. It's simple, but it needs some explanation. So what I'm going to do now is we will read the definition of the yield, and then we will see an example to explain it in more detailed way. So the yield is the number of moles of the desired product, which is the actual case, what happens in reality, over the theoretical number of moles of desired product. And this theoretical number of moles are calculated with two assumptions: that there is no side reactions and that all the limiting reactant is consumed. So it seems like a somehow difficult definition, but it's not that difficult. We'll just look at this example and things would be very clear now. So we have two reactions. The main reaction is A plus B go to C and D, and there is the side reaction where A plus 2B go to D. So these are two reactions that take place, and that the for two reactions the feed to the reactor that these reactions take place in is 100 moles of A and 150 moles of B. So we have two cases now, the ideal case and the actual case, and for the two cases we have the two reactions. And now let's discuss the ideal case, which is the most optimistic case, if what we hope will happen with 100% efficiency. So the ideal case, the 100 moles and 150 moles of A and B are fed to the reaction. The limiting reactant is A. It's very clear. So if the reaction go to completion, then all the A is consumed with 100 moles of B, producing 100 moles of C, and we end up with no A, 50 moles of B and 100 moles of C, and there is nothing that takes place, or no A and B are consumed in the side reaction, so there is no side reaction, and then the output of D is 0. We don't have any D, we have only B and C. So this is the ideal case. This is the ideal case, the theoretical number of moles of C that are produced. So this is what we meant by the denominator in the yield equation. It is the theoretical number of moles of the desired product, which is C is the desired product, the theoretical number of moles of the desired product formed, assuming that there are no side reactions, like in this case nothing happened, so there is no side reaction, and that the limiting reactant is totally consumed. Okay, so this is how we define it, the denominator. For the actual case, things would be different. So in the actual case, I have the same feed, but we can have 80% of A is consumed in the main reaction, and 80% of B is consumed, producing 80 moles of B and 80 moles of C as well. So the output from the first reaction is 20 moles of A, 70 moles of B, and 80 moles of C. In the same reactor, we can have part of A and B consumed in the side reaction. So in this case, we will have these outputs of the main reaction. I'm just zooming in to make sure that things are visible here. The 20 moles of A are still there in the reactor, so 10 moles of them are consumed to produce 10 moles. And these 10 moles react with 20 moles, so 70 minus 20 is 50, and C is done already, and we will have 10 extra moles of D. So what we have actually produced in this reactor is 80, theoretically is 100. Okay, so this is the ratio between what actually is produced to the number of moles that are ideally or would be ideally produced, is what we call the yield. So I'll go back to the definition just to take a look at it one more time. It's the number of moles of the desired product divided by the theoretical number of moles of desired product formed if there are no side reactions and all the limiting reactant is consumed, multiplied by 100%. And of course the range of the yield would be from 0 to 100%. So this is very very easy. Now the second parameter that we use to describe the deviation from the ideal case is called the selectivity, which is the number of moles of the desired product divided by the number of moles of the undesired product. So in the example that we just discussed, it's going to be the 80. Okay, let's zoom in again. It is 80 divided by 10. So it's C is the desired, 10 is the undesired. So it's 80 divided by 10, so it's going to be 8. Selectivity can be any value. It can go up to 10, 20, 30, 100, whatever. And of course, as it gets bigger, it's better. Because this means that we have a very big difference between the number of moles of the desired product and the undesired product. So let's apply this to what we have here in these equations that we have. These are the same equations that we started with in this video. So if we put symbols for ethane to be E, ethylene to be ETH, methane is M, propylene is P, then the yield, of course, the yield is going to be for the desired product. It is the number of moles of ethylene generated divided by the number of moles of ethylene that would be theoretically generated. So we have here this denominator, which seems a little weird, but it's very very simple. If you think of the number of moles of ethylene that would be theoretically produced, you just look at this equation. It's if this is, let's say, 10 moles, then it's going to produce 10 moles. If the 10 moles are totally consumed, then they produce 10 moles. If this is 50, it would be 50. So it's the same number. And the way we say it's the same number, because the ratio is 1 to 1, so multiplied by the coefficient of ethylene divided by the coefficient of ethane. So the general equation is this: you multiplied by the coefficient of ethylene divided by the coefficient of ethane, and you multiplied by the negative sign because this is -1, it's not 1. We said the coefficient of the reactant is negative, so this is let's say it's 50, so it's 50 multiplied by 1 over -1. So this is going to be negative, so we put a negative sign to make it positive again. You don't need to use this formula, it just depends on the common sense. You can say it's 100 to 100, so, or 1 to 1, so it's 100 to 100, so it's fine. So this is the yield. The selectivity, we can have more than one selectivity because we have two side products. We have methane and we have propylene. So we can have selectivity of ethylene to methane, and we can have the selectivity of ethylene to propylene. So this is the number of moles of ethylene to methane, number of moles of ethylene to propylene. Okay, so this is all for this video. I'll stop here and we will continue talking about the multiple reactions in the next video. So I'll see you then. Goodbye.